Welcome to the Tutte Colloquia. I'm very happy to introduce Kate Larson, who is a professor and a university research chair in our Cheriton School of Computer Science, and is also a research scientist with Google DeepMind. So she's interested in algorithmic questions arising in artificial intelligence and multi-agent systems, with a particular focus on algorithmic game theory and computational social choice, group decision-making, preference modeling, and the insights that reinforcement learning can bring to these problems, along with ways of promoting and supporting cooperative AI. So I'm very excited to hear the talk today. Please take it away.
Okay, thank you so much. Thank you very much for the invitation to speak. And this is the first time I've actually talked about this line of research, so I'm a little bit nervous because the slides are very, very new. I'm also going to spend quite a bit of time kind of motivating the work, so like why we're asking the sorts of questions that we're asking. This is, as you said, I'm over in the Davis Center in computer science, and I also spend some of my time with Google DeepMind, based out of the Montreal lab and also associated with the game theory team. And this is joint work that was mostly done inside Google DeepMind with a whole bunch of people, some of them with Google DeepMind, some of them at other institutions. So we're going to call it soft Condorcet optimization. So the Condorcet bit is important. So in particular, I'm going to be drawing on ideas from social choice theory. So we're going to form the foundation of the sort of methodology that we're trying to develop and promote. But as I said, I'm going to start with motivation. And one thing we've become really interested in over the last few years is evaluation. Okay? And particular sort of general agent or model evaluation in the context of AI. So it's become no surprise to anyone in this room that progress in artificial intelligence is measured very, very much empirically, and has been from the very start of time, from sort of Turing's sort of first paper and some of the checker programs that came out soon after. And so we spend a lot of time measuring performance of our agents, of our models, or our systems, sort of on common benchmarks as well as common problems. Again, there's a long history of this inside games. Games is one of the most sort of well-known form of sort of AI research, partly because it's fun, but also because we could actually do evaluation sort of quite elegantly there. But a lot of the progress particularly recent progress in AI has been driven by having common benchmarks. So again, this goes back for quite a long period of time. So the UCI machine learning repository has been incredibly important sort of over the last few decades in making sure that we had standard data sets on which to train our machine learning algorithms. And then more recently have ImageNet, which is a massive data set of labeled images, which is argued as one of the reasons why we saw this explosion in deep learning. And then more recent repositories such as Hugging Face, which allows everyone to sort of work with these common benchmarks and do evaluation. Large language models are sort of where a lot of the excitement is at the moment. And of course, sort of the evaluation questions around large language models is incredibly important. Probably the platform which gets the most attention at the moment is something called LMSys and its chatbot arena. I'll talk about that in a few minutes, sort of how that works, give you an example. Now, for those of you who are sort of interested in AI, but maybe have an outside perspective, you might see the results of these evaluations, for example, in Chatbot Arena, sort of published sort of openly. You might have been following the progress that was made with AlphaGo and how it was doing against Lee Sedol in the various competitions. But what's important to remember is that before an AI agent or a system or a model, I'll be using those terms interchangeably, is released, there's a significant amount of time and compute is spent on just looking at evaluation, trying to measure how well it's performing. And this is massive amounts of data that's coming in. We have data coming in from a variety of different sources, be they auto raters, sort of these various game leagues that they run across multiple systems. There'll be multiple checkpoints, parameter sweeps, and so on. So you get this massive amount of data, which then people are trying to understand and evaluate which model or which system or which agent is performing well in what context, and then what does that actually mean. So when we talk about sort of general agent or model evaluation, the sorts of questions that we're asking is, given this massive amount of data and signals we're getting from all these different sources, what's the best agent? Okay? is agent X better than agent Y? Is model X better than model Y? What happens if I am interested in model X, Y, and Z in different contexts? Can I do some sort of comparison across them? And why are we asking questions like this? Well, we're asking questions because we want to know, which ones do we then allocate more resources in order to refine? Maybe train a little bit more. Which ones are released? Which ones are held back? Which ones do we have to go back and rethink the entire design? So the decisions are being made based on the evaluation outcomes and how we're doing the evaluation in the first place. So you may say, well, why is this hard? One of the reasons why it's hard is that it's sort of not a well-formed problem, right? So the questions that we're asking is, well, is X better than Y? Well, what does that even mean? Better in terms of what? We're often trying to aggregate data that is coming from lots of different contexts. And I'll give you a concrete example of that, and sort of in my next slide. But in particular, what we might be doing, not only is the data coming, we're trying to aggregate data that's coming from different contexts and different settings, we're trying to score, for some definition of score, these agents or models or systems across possibly different tasks, right? And there might not be any systematic way of doing that scoring, and so we have all these numerical values that really should not be compared. So we cannot do simple approaches like weighted averaging. If you begin to do that, things get problematic. You're not actually capturing the right aggregated information. Often our data is very unbalanced. And again, a point that I will come back to in a couple of slides is that currently one of the predominant ways of doing kind of evaluation and ranking or rating different models or agents are often ELO-based. It would be ELO or Bradley-Terry models. And these are not necessarily designed for the use case at hand, for the evaluation context. They're very good in some settings, but the settings that we are finding ourselves trying to do evaluation in is not actually what ELO was designed for. And so we begin to see some problems. So to make this more concrete, let me provide you with an example. This is data that's relatively old now, 2017, that came from the arcade learning environment. So those of you who are, I have a bunch of my students here, so the AI students might be familiar with this. This was an interesting environment where you could go, you could take your reinforcement learning-based agent and see how well it does playing Atari games. So this was actually quite famous because Breakout was sort of one of the first really, really cool uses of an agent learning how to play an interesting game, kind of just from scratch. Now, what this environment does is that it actually has 54 different Atari games, and what you can do is that you kind of bring your algorithm or your reinforcement learning agent to it, and then play, and then see how well you do. And so then you would get data like this. So we have all our different games, have a different set of different agents, and what's important is that across all these different games, they all have different scores. So from Breakout, the scores range from about 345 or so up to like 680. But in Demon Attack, we're looking at scores in the hundreds of thousands. Pitfall, we have scores in the negative numbers. And so you can't really compare these scores across kind of these different games, these different tasks. It's sort of non-comparable. We also are interested in generalization. We want to know, well, which agent is the best? So the best at playing Atari games. Well, it's unclear. Rainbow looks pretty good here. It wins lots. All the numbers in bold are sort of correspond to the highest score. So Rainbow as an agent looks pretty good, but it doesn't win everything, right? Arguments could be made that maybe we really care about Demon Attack, in which case A3C is maybe a better agent. So this data is kind of complicated. Even though this is quite a simple setting, this data is actually quite complicated and be unclear how to then kind of rank these different agents and answer the question, which is the best, which generalizes the best. Another example, and this is sort of in the large language models, is sort of LMSys or Chatbot Arena. Does anybody follow evaluating of Chatbot Arena? Right, so inside this is, okay, so you can actually go to the Chatbot Arena and you can rank models. So all the big large language models are on this. And the organizations pay a lot of attention to the rankings. There's a lot of investments going in making sure that these different models rank well. So how does it work? Well, these models are submitted. Then anybody can just not even log into the system, anyone can just go to the web page, and you can enter in your prompt. It's kind of fun to do, some sort of prompt, or a picture and ask a question about it, and then 2 models will be selected, and then they'll generate some response. And then you, as the person on the chatbot arena, will vote which one was better. Okay? And then, this is done by people all over the world. You get to decide on what prompt that you're going to do, so there's no control here. And then what they do is that they take these sort of up-down votes, or sort of, model A is better than model B, and they use it to compute a score, which they then rate or rank these different models on. So before the start of the year, the ranking was just entirely ELO-based. More recently, this past year, they've now changed the ranking. It's sort of using that Bradley-Terry-based model, which is very, very similar to ELO, but it's basically an MLE of ELO, just making some assumptions as that there's some fixed sort of unknown pairwise win rate that's going on. But what's critical here is that we have an example of an evaluation framework, and decisions are being made based on how well these different models actually rank, or actually rated or ranked on this system, including which model gets sort of more training resources, which ideas are scrapped, which will go ahead further, as well as boasting rights. So there's a lot of work happening behind the scenes to ensure that some of these models, whether they're from these different organizations, rank highly. So these evaluations and these things actually matter. So let's just take a little bit of a side note, and we'll talk a little bit about ELO ratings, because I'm going to then come back and say, well, we have some concerns about ELO, and we're going to sort of propose something different. So what is ELO? Anyone who plays chess competitively will know about ELO. It's just a method that was developed, I forget, maybe in the 60s, for calculating the relative skill levels of players in non-zero-sum games. So that was the use case. The use case was chess. And what you wanted was some way of rating chess players. And so this is ELO ratings. And so the difference between your ELO ratings between 2 players we can interpret this as a predictor of the outcome of a match. So what is the probability if we have 2 different ELO? If your ELO score is higher than mine, then we predict that you are going to, when we are paired up to play against each other, you're more likely to beat me than I am to beat you. And in particular, we have a formula. So what we're trying to do when we are computing ELO, we're trying to compute this rating R, and it's assigned to some player such that this particular equation holds, where this probability is sort of the win rate, the probability that I has beaten J, sort of based on this historical data, right? And we're just sort of fitting this equation to figure out kind of what the various ratings should be. Okay? There's lots of nice things about ELO. Again, it's well used, right? So in chess, as well as some of the sort of the esports settings, it's very simple. It's used to estimate kind of win rates between pairs of agents. So if I know your ELO ratings, I can kind of estimate kind of the probability that I'm going to be beaten by you. It can be formulated as an online algorithm. So basically, we don't need to batch. We can just, as our data comes in, we can just update the ELO scores. That's kind of convenient. But there are also a number of well-documented drawbacks of using ELO. The first is that it was designed for 2-player zero-sum games. But often in the context where we're doing evaluation, we are not talking about 2-player zero-sum games. We actually have whole sets of players, which are maybe sort of playing, well, I've had some examples where we're playing 7-player games. Or with like the large language models, we're evaluating them in very, very different contexts because the prompt is sort of the context, and because the prompts are really different, it can become unclear whether sort of ELO is actually capturing kind of the right things. Another well-documented problem with ELO is that it cannot handle situations where you have sort of intransitivities in your data. So you have cycles in your evaluation data. But when we look at evaluation data, we often do have sort of interesting cycles. So maybe A is considered to be better than B is better than C, but then C is better than A when we do the pair off. And ELO is just not designed to be able to handle things like that, even though this is sort of a property that we see all the time. So going back to the evaluation problem that we've been thinking about, now we're sort of looking at tables of numbers like this, and we said, hold on, forget about these scores. These scores are not that interesting. They're not really meaningful. I don't know what minus 0.01 means in ice hockey. What's interesting here is the ordinal structure, right? It is I don't care what the score is, but it is interesting to me that distributed DQN did better than dual DDQN, which did better than A3C. Right? It's the ordinal structure I care about if I want to answer questions about which was the best general player. And so maybe what we can do is that we can reformulate this evaluation problem, toss out this cardinal scores, and only look at the ordinal structure. Now, if we're looking at the ordinal structure, and you're me, the first thing you think about is like, well, it's a social choice problem. We're going to vote. And so we've been arguing that the insights from social choice theory might be useful in the evaluation context. So in particular, what we are going to do is that we are going to reframe the problem and also the vocabulary a little bit. And in an example such as the arcade learning environment, we're going to say we have tasks, but really each task is going to be a vote. Okay? It's going to correspond, or voter, and it's going to correspond, and what it's going to be voting, the information we'll be sharing, is this ranking over, in this case, or all the agents, so based on how well it did in that particular task. So in breakout would have one ranking. In ice hockey, that's going to be another voter, and it's going to have a different ranking, right? But we're just going to use this ranking information, and then what we'll do is that we're going to aggregate this ranking information, interpreting them as preferences, and then apply social choice theory, and try to see, well, what rankings are going to arise. We can move away, just as a side note, so data like this, it's very easy. We can also use a similar idea if we are in sort of more of a game setting where we are asking, well, did agent 1 do better than agent 2? And some like pairwise comparisons, we'll say, yeah, that's fine, we can handle that too. We'll just consider that. And now an outcome will also then just be a vote. A is better than B, or maybe A was better than B, better than C in this particular setting. Okay? So now evaluation data, we're going to transform that into votes. And then because we now have votes, we kind of have a whole sort of machinery, 200 years of thinking about how to aggregate ordinal information in the form of votes that we can begin to leverage. Okay. So we've been calling this voting as evaluation. And we do have like a paper which talks about this in the archive. And so, as I said, we're going to be leveraging ideas from social choice theory. So social choice theory is just this mathematical framework that allows us to reason about really group decision making, but really focusing on situations where there is some underlying ranking or ordinal information that we're trying to aggregate to come up with the right decision or the right sort of final ranking. So in particular, we're going to be leveraging ideas from voting theory, and there's a number of reasons why we think that this is going to be useful. What's nice about social choice and voting theory is that it's really old. As I said, people have been thinking about voting problems for a long, long time, but in particular, since about the late 1700s, people have been writing and thinking formally about what it means to aggregate ranked information. Much of the work is axiomatic in nature, right? So we have these properties which are really carefully and crisply defined, and we also have a clear understanding as to what properties are compatible with each other and what properties are not, so what you can achieve and what you cannot achieve, as well as understanding when we say, okay, we're going to aggregate our preferences, our votes, or our rankings over these agents or models, we're making a choice as to what voting rule or aggregation rule that we're using, and associated with that choice will be a clear description as to what properties you're going to guarantee and what properties you cannot guarantee. So we can then look at our outcomes that are returned by our aggregation methods or our voting rules and describe exactly why certain decisions were made. So we kind of have this idea of we give axioms as explanations. So we have sort of like justification as to why we're ranking one way versus another. Said we're using voting, so this allows us to work with ordinal information. So this allows us to move away from scores, which can be noisy or just not necessarily meaningful or incomparable. So it means that we don't have to worry about sort of normalization or averaging. We can't even average, doesn't even make sense in this context, so we avoid it. And then also, the evaluation context is actually a really interesting use case for some of the ideas that have had sort of more theoretical, have been thriving theoretically inside the social choice literature, but maybe haven't seen much practical application. In particular, there's a branch of social choice theory which looks at probabilistic voting rules, which have a whole bunch of really nice properties and allow us to circumvent some of the impossibility results like Arrow's theorem. But in practice, if you're thinking about elections with people, you'd never use a probabilistic rule. But in the evaluation context, suddenly, why not? It becomes sort of interesting test cases that we can explore in a grounded application. Okay. So let me sort of look at an example as to this is our Meeple's pentathlon, which we're very fond of, and also the one particular property that social choice theory allows us to talk about and provides us justification for some choices that we might make. So in my Meeple's pentathlon, I have a bunch of Meeples who are competing in the pentathlon. They're all competing across different sports. So we have, badminton, they have to do badminton, and then they have to do synchronized swimming, and so on and so forth. All these sports are scored in different ways. They decide their winners in different ways. One's based on speed, one's based on artistic expression, and so on and so forth. So what we can have is that we'll have rankings based on how well they did in these different sports. And now we want to come up with who was the winner of the pentathlon. So in practice, this is often done by assigning different scores and then sort of doing using some sort of scoring rule. But we're just going to say, no, this is a vote. So we have archery be 1 vote, says that A is better than B is better than C. Synchronized swimming says, no, C was better than A than B. And what we want to do is we want to aggregate this information. There's lots of different ways we can aggregate. One particular way would be looking for rules that allow us to choose what's called the top rank, the Condorcet winner. So a Condorcet winner is it's a particular alternative or agent or model or meeple in this case, which is kind of agreed upon should be the winner, should be the top ranked agent. So it says if an alternative A beats every other alternative in a pairwise comparison, then it sort of makes sense that A is the best, right? It can beat, you pull out anybody else and it's going to beat it. We see this pairwise comparison. So in our little pentathlon, so C is going to be our Condorcet winner. Why? Well, we compare C against A, and we see that 3 out of the 5 competitions, C beats A. And then C against B, well, again, 3 of the 5 competitions, sort of C beats B, right? And so C is always the dominant player somehow. So C is the Condorcet winner. And so we can all argue, yes, C is the best one. Now, Condorcet winners don't always exist, but we'll worry about that later. We can handle that with probabilistic rules. Now, what we could have done is that we could have, so if we had a voting rule which was guaranteed to return the Condorcet winner, and such if it exists, and there are rules that can do that, like for example Copeland, then C would be our winner, would be our best agent. If instead we did something like ELO, because the actual win rates between player A and meeple C are actually the same, if you just the number of wins losses, then our ELO would say no, A and C are equivalent. So we already see a disconnect between kind of what ELO would rate, how would rank these agents or rate them, and how sort of a social choice methodology would rate them. We have other examples that I'll visit a little bit later, which sort of shows us even a sort of more extreme difference. There's also lots of other properties that we can adapt from social choice into the evaluation context, like population consistency, but really in this talk I want to focus on this idea of Condorcet winners. Now, so in principle, we can use social choice and these voting rules to, aggregate this ranked information in all sorts of different ways and have sort of properties that we can then go back and point to sort of justify our ranking decisions. But we do run into a problem, okay? And in particular, we want to be able to handle large, sparse data sets because, as I said, we're often running in situations where we have lots and lots and lots of evaluation data over potentially lots and lots of alternatives, and so we're going to need methodologies that are going to scale. So here's a sort of a nice little application that we have been playing with. There's the game Diplomacy. So the game Diplomacy is sort of a really complex game. It's a 7-player game. And there's interesting data sets available. So the web diplomacy data set has an outcome of games that were played online between over 11 years. Okay? These are 7-player games. So in this data set, we have about 31,000 games with their outcomes. An outcome is a ranking over the 7 players. And like almost 53,000 players. Now, this is very sparse. You don't actually, not all players played against everybody else. But we still might want to be able to take data like this and be able to talk about relative rankings. So maybe agent 337 and agent 98 never played against each other, but I'd still like to be able to predict, is agent 337 kind of better at diplomacy than agent 98? But the data is so sparse that these sort of more classic voting rules that come from the social choice literature just really couldn't handle it. So am I doing? But still, we went back to the literature and we said, okay, what is this problem? We want to be able to maybe predict, okay, how, the relative ranking, so how we're going to evaluate these different agents, but we might not have enough data, but we will have some data. So maybe we can imagine a case where we're actually working sort of with underlying where we have sort of noisy samples from our sort of underspecified data. And there does exist some true ground truth ranking over all these agents, all these diplomacy things. It's out there. We just don't know what it is. And then each of us are going to have different views. So maybe I have seen a few games of diplomacy, and so I have some notion as to how these agents are playing against each other, at least some subset. And that could be my vote. And maybe Manfred has seen a few different games, so he has some other data, maybe with different agents. They're not all of them, but he can then sort of incorporate and sort of submit, if he's seen a game, he can submit that information. And so we might be able to get these sort of, these samples. Okay, can we do voting with this? And what's interesting, if you look back at the literature, that this idea that there is some, objective ground truth out there, and that what our voters are doing, they're not submitting their preferences, instead they are just submitting kind of noisy samples that they have of that ground truth, is actually a really, really old idea, and one of the original ideas that sort of motivated a lot of the work in voting. So in particular, Condorcet, who was writing in France sort of in the late 1780s, was thinking about models like this when he was talking about his jury theorems. Where again, this idea that there's ground truth, and what a voting is simply a way of aggregating noisy samples in order to uncover what that ground truth is. This actually idea even goes back much further. So you look at the writings of Lull from the 1300s. When he was talking about voting, he was also using the same idea that voting is a way of uncovering truth. Now, they didn't have the math to talk about sort of the, what this would mean mathematically, but the ideas have been out there for a long time. Now, more recently, again, a little bit of divergence, but sort of building up to sort of the models that we work with, people sort of began revisiting Condorcet's sort of model of sort of this objective voting, where our votes are just noisy samples, and then we're trying to aggregate them to recover a true ranking. And then Kemeny in 1959 proposed a new voting rule that actually had, it's hard to compute, so computationally hard to compute, but was an interesting idea. His voting rule, so the Kemeny rule, says, okay, I'm going to give a set of votes, so these rankings over these alternatives, and then the ranking that I'm going to return, which I'm going to call R star, is going to be the one which minimizes this average Kendall-Tau distance to all the votes in V, where this Kendall-Tau distance is just a function which sort of counts the number of discordant pairs between sort of ranking 1 and ranking 2, or basically the number of actions you have to take if you're doing kind of a bubble flip operation to move ranking 1 to ranking 2. Okay? And it's a voting rule, so given a bunch of votes, what I can run through this Kemeny procedure, and then I'll return a ranking over my set of alternatives or agents or models, which minimizes this average Kendall-Tau distance. Okay? And it has some nice properties. In particular, if there is a Condorcet winner, something that we care about, it's guaranteed to top rank it. So again, if I look at Meeple's pentathlon, and I want to find the rule that be returned by Kemeny, I'll call this my optimal ranking. Well, given this data, my optimal ranking would have C first, A second, and then B third. And what I have here is just sort of the Kendall-Tau distance between each of the rankings in my pentathlon, as well as my optimal ranking, right? And so, CAB and ABC, the Kendall-Tau distance is 2 because there are 2 discordant pairs in that case. Whereas between CAB and CAB, obviously the Kendall-Tau distance is going to be 0. So this will be we'll call this the optimal ranking, the one that will be returned by the Kemeny rule. Now, Young actually made the connection between this Kemeny rule, which was proposed not necessarily thinking about Condorcet's jury theorems and the sort of this maximum likelihood estimation, but was just sort of an interesting way of returning rankings given a set of votes. But Young made this connection between sort of Kemeny and Condorcet's original jury model. And it said, okay, let's V star be this ground truth ranking that we don't actually know. And we're going to assume that the votes or the rankings that we are drawing and that we're going to use to aggregate are distributed according to some distribution which is proportionate to 1 over the Kendall-Tau distance from our true ranking. So I'm more likely, if I'm a voter, I'm more likely to observe a ranking which is close to this true ground truth, as opposed to like something really, really far away. It's the only requirement that we need. He then showed, well, the ranking produced by this Kemeny rule, minimizing the average Kendall-Tau distance, is the maximum likelihood estimation of the ground truth. Okay? So now this gets us to our model. So I said I was going to spend a lot of time on motivation. So I like history, so we're doing this. So we said, okay, we want to be able to rank, but we want agents. We're going to have this messy data, so our data is inherently going to be noisy. It's going to be sparse. We want to be able to, but we still want to be able to have some guarantees as to how we are aggregating this information. Okay? But what's going to be, we can't run Kemeny-Young because that's definitely NP hard. It's like order, I think, n to the n. It's just, we're going to run out of compute. We want to do this on large data sets. So what we have proposed is something called soft Condorcet optimization, where we're going to rephrase the way we think about computing kind of Kemeny-Young rankings, but using kind of ideas from optimization. Right? In particular, trying to understand whether we can use stochastic gradient descent or other optimization techniques while still maintaining some of the social choice properties, in particular as top-ranking Condorcet winners wherever possible. So at a high level, what we are doing is that we say, okay, give me a set of agents, models, alternatives. I'm just going to define some parameter vector theta. I'm just going to assign a score to each of the agent. Okay? Now the scores are actually not important. What I really want to do is I want to be working in ranking space, so in this discrete space, but I'm going to be using sort of optimization techniques, so I'm going to sort of have this score. Now what I want to do, I'm going to get some voting data. So these will be rankings over my alternatives or partial rankings. I don't actually require full rankings. And then I'm going to update the parameters so as to minimize a particular loss function. And then what we're going to hope is that by carefully constructing our loss function, we will allow us to inherit some of the social choice-inspired properties from the social choice literature, so that we can at least say the rankings that we are returning, sort of given this optimization procedure, are kind of the correct rankings, or at least are returning kind of, are the correct rankings based on a set of properties that we can specify beforehand. So most of it is just defining the objective. So we're going to have a set of alternatives. Again, these could be agents. They could just be alternatives. They could be models, whatever. We're going to have some parameter vector. Again, the parameter vector is useful for us because it allows us to encode a ranking. So these values serve only to determine a ranking over alternatives. So if alternative A is considered to be higher ranked than B, then it must be the case that theta A is greater than theta B. We're going to have a bunch of data. Our data is just going to be votes, where our votes is just a permutation over alternatives or a permutation over a subset of the alternatives. We can handle either case. And then we're going to introduce a misclassification indicator. Okay? In particular, it's just binary, so it's an indicator function, so it's either 1 or 0. I'm going to return a 1 if theta B minus theta A is greater than 0 in a particular vote that I have been given. So I'm going to get a vote. I'm going to see where A and B are sitting in my vector, and then I'm going to sort of see, okay, is that value greater than 0 or not? Return a 1 if it is greater and the 0 otherwise. Okay. And then I'll be able to find a loss function. So what I want to do is that given a set of votes, so again, these are going to be sort of permutations over A, or my set of alternatives A, or some subset of the alternatives A. My set of alternatives, my voters, and then my parameter vector. What I want to do is that I want to minimize this particular function right here. So it's going to be the sum over all the votes, and then for each vote, the sum over sort of these misclassifications. And if you stare at that long enough, you'll see that this actually, the sum over these misclassifications is actually the Kendall-Tau distance between V and the ranking induced by our current parameter vector. Right? So we're actually kind of, basically doing the same. If we are working directly with the rankings, we're just doing computing Kendall-Tau, but instead what we're doing is that we are working in this parameter space. But we are, really just computing Kendall-Tau. And we want to minimize the loss. So our loss function is minimal when the average Kendall-Tau distance between the votes, or the data that I've collected over time, and the ranking induced by our parameter vector is minimized. So we're going to be trying to sort of update these parameters, which will then induce the ranking, which is consistent with minimizing kind of the Kendall-Tau distance, given our set of votes that we have trained on. Now, of course, the problem here is that our indicator function is discrete, okay, and we can't handle that, so we're going to have to do some form of, of softening. So we're going to replace our indicator function with a soft approximation. In particular, it's going to use a sigmoid function. Okay? And so our soft sort of Kendall-Tau sigmoid loss will take this form, so exactly the same form as we saw before, where our loss function, where we minimize that loss function, it would result in minimizing our Kendall-Tau distance. All we're doing now is that we are just sort of now have sort of something which is going to be differentiable. It's a sigmoid loss. Okay, now we're going to try to minimize that. So the question that we have is, this kind of makes sense. So what we want to do is that we want to make sure that we're going to generate rankings which somehow have these nice social choice properties. And this way of formulating our optimization problem is going to lead to somehow the right rankings. So in particular, we're able to show that if given our set of preferences, so our rankings are partial rankings, there is some candidate there, which is a Condorcet winner, then, once we find the global minimum of our loss function, the alternative, which is top ranked, is going to be the Condorcet winner. So we can guarantee that. So if there is a Condorcet winner and we are able to find the global minima of our loss function, then we're going to return the Condorcet winner. Okay. There's some other properties I won't go into in much detail for sake of time, but this allows us also to move away a little bit from ELO and the Bradley-Terry models. ELO and Bradley-Terry are based on pairwise comparisons, which causes some limitations. I mean, there's some certain interesting properties that they cannot satisfy unless you insist on having transitivity in your data. Because we actually have a distance-based probabilistic ranking model, that just gives us a little bit more flexibility, and we actually have some nice properties. And I can talk about those later, but we're just inheriting things just because we are not restricting ourselves to pairwise comparisons. We have a richer model. Now, of course, the problem is going to be, how in the world do we actually compute? How do we solve, can we minimize this loss function? Okay. The loss function is our soft Condorcet optimization problem. The loss function is the sum of sigmoidal functions, which does cause a few problems. But there is the thing called sigmoidal programming, so you can formulate it as a sigmoidal programming problem and then apply kind of branch and bound. It doesn't scale particularly well. There are some massive scalability issues I'll talk about, sort of highlight when we get to the experiments, but in principle it works. In practice, what we will do is something called just stochastic gradient descent. Again, I'm working for a bunch of machine learning people, so this is what we know what to do. Stochastic gradient descent, given our loss function, is not guaranteed to converge. Okay, so we might no guarantees that we would actually return sort of the Condorcet winner if it so exists as top ranked, but it tends to work really, really well in practice. Another approach, again, I can talk a little bit about this afterwards, because I do want to get to the experiments, is just to change the loss functions slightly. Instead of having a loss function which is directly inspired by Sir Kemeny-Young's result, and using this Kendall-Tau distance as basically what we're trying to minimize, is that we can use ideas from perturbed optimizers and use something called Fenchel-Young loss, do Fenchel-Young loss optimization. So these perturbed optimizers allow you to do sort of optimization for settings where you might want to do some like sort of sorting, or also being used in some ranking things. And what you do is just transform your like sorting function into a smooth version by adding some carefully chosen noise. And then on that perturbed function, you can do gradient descent because it has sort of nicely convex in the parameters that you care about. So again, Quentin is sort of the expert on this, but we can reformulate it so we get a Fenchel-Young loss formulate a Fenchel-Young loss optimization problem, and then do stochastic gradient descent, where this is actually the gradient that we're using. It tends to be very, very fast to compute. It works remarkably well. However, this is a different loss function than our soft Condorcet optimization, and so we no longer have that guarantee about top-ranking Condorcet winners, though in practice it works really well. So now my last few slides, I just want to sort of talk about the empirical evaluation, because it's it was an interesting exercise in thinking about how we can get social choice properties sort of in this sort of almost sort of machine learning or optimization context. But the question is, of course, does it work? So, take a little game like this, can we recover the Condorcet winner? The Condorcet winner is C. ELO, as I already pointed out, is going to have a problem here. It's going to say, oh no, A and C are both, we can't just differentiate between them. All of our methods, whether we use sigmoidal programming, stochastic gradient descent, or Fenchel-Young loss, they all would top rank C. Here's another example. So imagine a case, so again, we have three alternatives. We have two voters that like A more than B more than C. Three voters think, no, it's C, it's better than A, it's better than B. The Condorcet winner, again, is going to be alternative C. Interestingly enough, ELO, in this case, ELO would top rank A over C. So if we ran ELO on this particular data set, we're going to say that A is better than C, even though Condorcet would say, no, C is better. Again, all of our methods are going to top rank C. We were interested in understanding, again, what the rankings that we are returning by doing the soft Condorcet optimization. How do they, first, do they return sort of Condorcet winners when they exist as top ranked? And also, how do they compare to this Kemeny-Young ranking? So if we applied Kemeny-Young's rules directly on the data and found the optimal ranking, how close is this soft Condorcet optimization going to be when it returns its ranking? To evaluate this, to measure this, we use the preflib library, which is a website which maintains lots and lots of preference data. So we did our evaluation over more than 12,000 preflib instances. And we divided it up into different sort of categories. So, M bottom was sort of the minimum number of alternatives. M top was the largest number of alternatives in that particular data set. We have sort of the size of all these different data sets, the average number of alternatives, the average number of votes in each of them. And then what we were really interested is understanding, what percentage of the time are we finding the Condorcet winner when it exists if we're using stochastic gradient descent versus sigmoidal programming. Also, what's our Kendall-Tau distance from the optimal ranking returned by Kemeny-Young compared to the ranking that we are returning, again with gradient descent or sigmoidal programming. So first thing you should note that sigmoidal programming did sort of bottom out after like 5 alternatives. We had numerical instability problems after that. The gradient descent basically just keeps on going. We find as long as we are below like 500 alternatives, which is a massive ranking problem, then with high probability we were returning the Condorcet winner, sort of like 92% of the time or more often with our approach. And our Kendall-Tau distance from the ranking that we were returning compared to the optimal ranking computed by Kemeny-Young was also very, very close. Again, we had to stop at 10 alternatives just because we could not run sort of Kemeny-Young after that. Again, it's too hard of a problem. And this is with massive compute resources. So, these soft Condorcet optimization approaches, even when you're running gradient descent, which did not have that sort of theoretical guarantee, was finding the correct ranking and top ranking our Condorcet winner when it exists. We're also interested, one of the motivations behind this is that a lot of the data that we look at is very sparse. We haven't run all evaluations, we haven't done all comparisons, we don't have full rankings. And so what we wanted to know is what happens if we have, how does sparsity in our data actually affect the rankings that we are returning? How robust are they? So we ran a series of experiments where we are simulating matchups like in a league setting. So in particular, we're sort of imagining that we had like a 4-player game, and then we're drawing players and having them play against each other and then returning kind of the ranking, like an outcome of the game would then be a ranking over those 4 players. We matched, this was in simulation, so we were controlling our data sets. We're using kind of a true skill like model. So each agent had an underlying kind of true skill, which was their parameter sort of theta I, which we then use to actually rank them. But their contest performance had a little bit of noise. So it was based on their actual underlying true skill with some sort of noise factor. And then we kind of compared them. We put them into contests in different ways. One was just we'd uniformly draw 4 agents and have them play against each other. The other set of experiments, we had skill matching contests where you're matched against agents that have had very similar skill levels as you. What we then saw is we then ran all these contests, and then we sort of looked, okay, what ranking would we have returned if we'd only seen a small subset of the data? And how does that ranking kind of differ as we have more and more examples? And so we'll just focus on the top ones. We're actually measuring the Kendall-Tau distance. This is the Kendall-Tau distance of the ranking returned by these different methods compared to the actual true underlying ranking that we were controlling because we were setting these parameters theta I. And what we can see is that we compared against a whole bunch of different approaches. The main thing, including ELO, which ELO does pretty well, but sort of what we find for our sigmoid loss and our Fenchel-Young, sort of sitting in here, we actually do pretty well. So even with just sort of a small fraction of the data, so we had 200 examples, if you even sort of seen like 50 examples, we're already beginning to see a drop in the Kendall-Tau distance. We're already getting pretty close to have a good estimate as to what the underlying true ranking is. And of course, this improves with time as we see more data. We also, actually I'm almost at, no, I won't talk about that. We can talk about that later. Basically saying the same thing. The last experiment that we ran, again, went back to that diplomacy question. And again, if you remember the diplomacy, we had a lot of games, a lot of players, but not very many comparisons. We still wanted to be able to ask questions like, well, is agent 1 better than agent 2? If they played against each other, can I say something about what that outcome would be? So this is, again, an evaluation question, but sort of speculative. Sort of a prediction as to what a relative ranking would be over some subset of the agents. So what we did for this experiment is that we took our training data, and this data that we had from the Web Diplomacy website, and we made it into basically like a sort of a standard machine learning setup. We created 50 random splits of data into training and test sets. So in our training set would have about 28,000 game outcomes, where a game outcome is going to be a ranking over 7 players. And then we held out about 3,000 games to test against. Okay? So what we would do is that we would take our training data. So another thing that we did is that we made sure that every agent or player that appeared in the test data also appeared in some case in the training data, but it was no case that an outcome that appeared in the test data also appeared in the training data. So we'd have data on agent 1, so we knew that had played some game. If it was in the test set, it would also be in the training set. But if we had in our test set that A played against B, played against C, played against D, that game would not be sitting in our training data. So we made sure to filter so that we did have different data there. At each iteration, what we did is that we would train, basically use our soft Condorcet optimization, compute it using kind of our training data, and then we would compare the ranking that we returned with the ranking in our test set, all the rankings in our test set. And then we sort of see, well, how did things work? Again, it would depend on the total number of iterations. The blue, so we have data for the Fenchel-Young loss, as well as our standard loss function, but where we're using stochastic gradient descent. What we can see is that we're measuring the Kendall-Tau distance on the y-axis, and as the total number of iterations increases, obviously, we see this nice drop in the Kendall-Tau distance. We also compared, and this is again, we are returning rankings which we're comparing against sort of our ground truth in our test data. We also sort of say, well, what would ELO have done? and then another voting method, which is our Copeland, which returns Condorcet winners. And, they kind of this flat line here, right? This 8.4, and we see a significant decrease in the Kendall-Tau distance. Okay. See a little bit, things begin to go up a little bit. We know that we were overfitting a little bit. There are probably ways that we could handle that better, though. But the proof of concept sort of was solving the problem that we wanted solved. Okay, so to summarize, so what I've done. So I spent a lot of time motivating, like why in the world would I care about ranking alternatives, particularly where we have sparse, noisy data. And it has to do sort of with this underlying problem of evaluation. We really, really want to know what model is better than what model and which agent is sort of performing better across potentially different contexts. And so what we are doing is that we have proposed sort of a ranking framework as an optimization problem, which is inspired by some ideas, some rich, very early, very old ideas coming from the social choice literature. But we can show that we can formulate this as an optimization problem, have some guarantees, and then deploy it in sort of interesting evaluation and prediction contexts. Okay? Now, there's lots of future work. We'd like to compare the soft Condorcet approach to other learning to rank methods. Right, so better understand kind of the sorts of rankings that we return versus some of the other learning to rank methods. There's also have been a number of proposals of ways of approximating kind of this Kemeny-Young rule. So we'd like to, again, sort of run some experiments where we compare our rankings versus these approximations, as well as other rankings inspired by tournament solutions. But while this would all be sort of in the more the evaluation and agent or model ranking context, we're also interested in another sort of problem, which is we see a lot of discussion on, has to do with LLMs and alignment. So right now there's a lot of interest in trying to make sure that if you have this large language model or foundational model, how do you make sure that it's behaving in a way which somehow best reflects the preferences of your underlying population that you're trying to serve? Right now, those models are often being kind of fine-tuned using basically Bradley-Terry models or things that look very much like ELO. We're curious in exploring the idea that if we can sort of have these richer ranking information, apply something like soft Condorcet optimization, whether that would then make a difference in the way that we can actually do alignment and the quality of outcomes that we can get. Okay, so I'm happy to take questions. That's fine.
Yeah, any questions? And wait for the microphone if you...
Thanks for the nice talk, very interesting. So a couple questions. First, the old theory, the Kemeny and the Condorcet, they didn't deal with sparse data, if I understood correctly.
No, they did not deal with sparse data, they dealt with uncertainty. So as we're getting is, right, so their models entirely has to do with uncertainty and if we have this noisy information. So while they do not inform us what we can do with sparsity, what we are finding is that we can handle the sparsity.
So, but is there a theoretical understanding then of what a winner should be for the sparse case?
Yes. There are, and this is something that I'd love to study, and we just haven't figured out quite how to do it at scale yet. When it comes to ranking and votes, there's an idea called necessary winners and, what's the other term? Not sufficient. There are ways of thinking about, so if I have some missing information, I can then figure out, okay, of these alternatives, who should be top ranked? And of these alternatives, who still has the possibility of being top ranked? Right? And there's a particular term, there's a literature on this. So I think an interesting idea or research agenda would be to see how this sort of necessary winners paradigm can then be translated into sort of when we talk about sparsity. So do I have enough data to actually identify who's a necessary winner, sort of top ranked, and who can I just rule out sort of early on?
Okay.
But yeah, we're thinking about that, but we don't have any good things to talk about yet.
Okay, thanks, yeah. And then the other is a technical optimization question. So I didn't exactly see your SGD, but I mean, it's known that SGD with constant step size doesn't actually converge, right?
Well,
So-
there's the temperature parameter which we are adjusting.
So you're shrinking the step size as you go along to make sure you converge?
Yeah,
Okay,
yeah.
got it.
And
Okay.
again, like in the paper, we talk, all of that's happening so that we do get those guarantees.
Other questions? I actually have one then, if we have some. So I noticed that your kind of softened version of the distance looks just like the probability from ELO. So if I interpret your theta vector as ELO rankings, it looks like you're kind of computing the sum of these probabilities. Is there a sensible interpretation that finishes that thought?
Yeah, there is. And again, so Manfred, who is this great student at University of Montreal, who's like graduating soon, actually did this really, really nice analysis that looked at the difference between kind of the updates that you do if you're doing sort of ELO versus the updates that you're doing kind of when you're doing the soft Condorcet optimization. And there are some similarities, but there are some subtle differences. And I'm going to have to refer you to the appendix because we wrote this several months ago, and I don't, so there's some subtlety there, but they're close, but there's a subtle difference. And again, the big thing that we are getting is that we are allowing for the possibility, so ELO is pairwise, right? And Bradley-Terry is pairwise comparisons, and that's really, really limiting. So with the soft Condorcet optimization, it's very natural now to have sort of more rich ranking information, which means that you can actually get a little bit more structure from the data when it's available to you, which then allows you to avoid some of the weirdness that we get, these sort of pathological cases that we're finding with ELO.
More questions?
Carter.
So you picked Condorcet as the kind of axiom to satisfy it. Is there any reason that you picked that axiom over others or other properties?
Well, Condorcet just seems really natural, right? Like if I tell you what a Condorcet winner is, then most people go, yeah, actually that makes sense, right? It is the alternative which, if I pair it against anybody else, is going to always win, right? What else should be the winner? So the attacks on Condorcet have always been about non-existence. There are going to be, there are going to be cases where there are some intransitivity, where the Condorcet winner might not exist. So we have to then fall back to something like maximal lotteries to talk about sort of like essential sets or bipartisan sets. But what other properties might we want? So I think I didn't talk about this in this talk, but there's like population consistency, which is an interesting property, which means if we're running some voting rule and I kind of have, this side you vote and this side you vote, and I aggregate the outcomes of those two votes, I'm going to get the same outcome as if I had you all vote in one go. So that's kind of a nice property, right? And so some of the voting rules are going to satisfy that, like the scoring rules satisfy that, but the Condorcet consistent rules don't. So if we want to guarantee Condorcet winners, then we're going to give up population consistency, right? We think so, right? But we understand when you can get one and when you can get the other, right? And so now it becomes a sort of a design choice. So we like Condorcet winners for this thing, particularly because we are thinking very hard about sort of these tournaments. But there are other properties which would be really interesting to explore and see what you could achieve. But population consistency, you run Borda. So.
Great, we're a little bit over time, so maybe let's thank you again.